We are closer to getting to the moon.
Good for NASA, good for America, good for all of us.
Robot drivers, start your robots!
Okay, so get that out.
We're replacing some of our rubber mounts.
Proceed Maverick team, Edcuation.
I think we did pretty good. We had a far break.
Future iterations of this competition.
Like trade school, no tech school.
Just to really take massive volume of record.
Now, the exciting Caterpillar Autonomy Awards, and first place is Purdue University.
Top prize for Robotic Construction Award, first place, is awarded to the University of Illinois in Chicago.
I feel great. It's all the credit goes to the team. It's a total team effort that made this work.
The Artemis Award for the 2025 Lunabotics competition is awarded to the University of Utah.
Yeah, but right now it's just surreal to think that we actually pulled it off.
Good morning and welcome to day 2 of NASA's 2026 Lunabotics Finals event. That video that you just saw was a highlight reel from last year, and boy was last year exciting. Well, I think we've got an even more exciting year in progress this year. We had a full day yesterday, day 1, and we're about to start day 2 of a 3-day competition. So, we are broadcasting live from this amazing Center for Space Education facility, which is inside NASA Kennedy Space Center's visitor complex here on Florida's East Coast. My name is Kurt Loit, and I'm a NASA software developer and robotics researcher, and I am so happy to be your MC, your narrator, and your color commentator for this event. I want to give a big shout out to all the teams and staff and the guests that are here in person at NASA. Let me hear it, people. Shout it out. We still got people coming in. It looks like there's a lot of empty spaces, but we've got 4 or 5 teams that are here getting ready for this morning's competition. But we're also super excited for all of you who are watching this broadcast from all over the world. Now, whether you're watching this live or watching the recording later, we want to thank you so much for your interest in NASA, for your interest in space exploration and lunar exploration, and for your interest in this event specifically. Please don't be shy about sharing our Lunabotics website with everybody that you know. The link to the NASA Lunabotics event website, if you don't already know, is go.nasa.gov/Lunabotics. That's go.nasa.gov/Lunabotics. And the links to all 3 of our daily live streams are right there at the top of that webpage. So just go to the NASA Lunabotics event webpage to find the link to each day's live stream. And we will be starting our live stream each day at 8 a.m. So make sure you set your alarm clock so that you don't miss a thing. Now, in case you're not familiar with NASA's lunar exploration plans, allow me to give a very quick high-level overview. A couple months ago, NASA's administrator, Jared Isaacman, he publicly announced that NASA would switch to an accelerated and phased plan that will relatively quickly build a moon base in the lunar South Pole region. The end goal of this new plan is a continuous and a sustainable human presence living and working on the lunar surface. Now, some may be thinking, well, we did that back in the 70s, so why do that again? And it is true that the accomplishments of the Apollo lunar program were quite amazing for that time. But that 70s technology couldn't sustain our astronauts living and working on the lunar surface for more than just a few days at a time. NASA's new lunar program, called Artemis, along with Administrator Isaacman's new accelerated and phased mission plan, gets us on a path toward an enduring human presence on the lunar surface. This plan unlocks the scientific, the technological, and the economic benefits of lunar exploration. And so it actually provides a path and a plan to support long-term, even year-long human missions on the lunar surface, which I find very exciting. So where does NASA's Lunabotics collegiate competition fit into NASA's overall plans? Well, I'm glad you asked. Lunabotics gives college and university student teams the task of designing and building working prototype lunar construction robots. During this competition, these student-designed and student-built robots are going to drive over complex and rugged moon-like terrain. And they'll dig and transport very fine particulate material or simulated moon dust from one location to another during a timed event. And we will measure the final volume of the pile of this simulated moon dust that each robot creates during their timed event. And you probably guessed that a larger pile gives the team more points. There are a lot of other variables, though, to be aware of that complicate the scoring and add to the challenge for these student teams. But I'll go over some more of those fine details as they come up during the timed competition events. I'm going to be here the whole time to help explain what's going on. We had 47 teams compete last week in the Lunabotics qualifying event at the University of Central Florida over in Orlando. And the top 10 teams from that event are right here, right now. These 10 teams that you can see getting ready for today's event behind me, they are right here, right now. These 10 teams are about to compete for the grand prize in NASA's Lunabotics 2026 finals event. Let's make some noise. Woo! All right, so if you missed yesterday, shame on you. Though it's all is not lost because you can go back and watch the entire broadcast. But what happened, let me summarize. What happened yesterday, we started with our opening ceremony, and then the team spent some time preparing the robots and getting ready to compete. And then we ran 6 teams yesterday. We ran the College of DuPage, University of Virginia, University of Utah, University of Illinois Chicago, Michigan Tech, and New Mexico Technology, School of Technology. I apologize, I forgot their official school name. But New Mexico Institute of Technologies, I believe. Those are the teams we ran yesterday. So if you're interested in watching any of those teams, and we had some amazing runs yesterday, go back and watch that footage from yesterday's live stream. And what is going to happen today? Well, as soon as our arena judges are ready to start, and as soon as our first team is prepared and ready to start, which could be within the next 20 minutes. That's our target, but we may be ahead of schedule or behind schedule. So we'll start when we're ready. What we're going to see is University of Alabama up first, and then roughly an hour later, San Diego State University. Basically, every hour we start a new competition run. So Alabama, San Diego State University, Virginia Tech, and Iowa State. Those are the last 4 of our 10 teams. There will be a lunch break in there, obviously, and then what happens from there, we will have run all 10 of our finalist teams through their very first run. Each team gets 2 official competition runs. So this afternoon, we will start the cycle over again. And so this afternoon, we will see basically the teams that we saw yesterday morning: DuPage, University of Virginia, University of Utah, and depending on the timing, we might have time to also get to University of Illinois Chicago. Those would be the second run for those teams. So that's what's on tap today, with the caveat that things are flexible, the schedule's flexible, even the order of teams running is flexible. So stay tuned and watch live, and I will update you with any schedule changes that happen. So don't go anywhere, And in the meantime, watch our live feed while we kind of tag along with the Alabama team as they prepare their robot and as the students prepare for their first run of this finals competition this week. So don't go anywhere. You're watching NASA's Lunabotics 2026.
250 years ago, 13 colonies laid the foundation for the greatest and most enduring democracy in the history of the world. One driven by courage, faith, and freedom. From that moment, we became a nation defined not by where we stood, but by how far we were willing to go. We conquered vast frontiers, invented tools that shaped a modern world. We found light in the dark, and we rose from the earth. Faster, higher, farther. We pushed beyond the sky and into the unknown. We carried our courage into the cosmos, and we planted the American flag on the moon, the defining achievement of American superiority in space. Today, our curiosity stretches farther than ever. American robots search ancient rivers on Mars. New telescopes unfold to glimpse the first stars. And a new generation prepares to return to the moon, this time to stay. For 250 years, America has carried the light of humanity forward. But American exceptionalism isn't inherited, it's earned. Our greatness comes not only from what we've done, but what we're still determined to discover. Because in every era, across every horizon, America is at its best when it's reaching for something greater. America celebrates 250 years, and we are leading the world into the future.
I became aware of Caterpillar at the NASA robotic mining competition. NASA has a goal to colonize the moon and Mars. So to facilitate a lot of those activities, you've got to be able to excavate the material. So as a way to crowdsource some of the ideas for how to build those excavators, NASA's created this robotic mining competition that Caterpillar is a big part of. Every single year we build this basically a robotic excavator, much like some of this stuff. I mean, we built a front end loader similar to that one year, and you pretty much have, I think they give you like 10 minutes and you go up and down the track and you mine and you bring it back and they score you. So autonomy is the big part of the competition now. In the past years, it's been all about, you know, being able to move in the material. The material is something very difficult to work in. But as teams have evolved, the competition has evolved, and autonomy is a key part of that now. And I think that's really one thing that sets our school apart. That's why we do so well. We have an edge on that autonomy perspective. So I think that's kind of what CAT's interested in us, honestly. Robotics is a new way to solve problems. So there's infinite possibilities to solve those problems, and you have a chance to make the world a better place. Honestly, you're developing technologies that make everyone's life easier. You're automating tasks. You're just making a better quality of life for everyone. I normally associated CAT with just this big, large construction type company, and it's really more of a tech company. Now getting to be inside and seeing all the innovative things that CAT does is I don't think people really appreciate all the technology that goes into CAT equipment. Kind of expected it to be a little bit of intimidating, honestly. You know, CAT engineers, you know, but it's a really fun work environment. I love coming to work every day, honestly. Caterpillar has a lot of opportunities to succeed. One of the things that's really stuck out to me that I've learned during my time as an intern, just all the opportunities within the company. I'm the kind of guy that likes to jump around. It's become apparent to me that within Caterpillar, if you want to have an entire career at Caterpillar, you have an opportunity to do all those different things and still stay within the company. You don't necessarily have to leave and hop jobs and things like that. All those opportunities are provided to you within the company. I would absolutely recommend the Caterpillar intern program to my peers. It has been a great learning experience that I'm very thankful for.
You are watching NASA's 2022 Lunabotics Finals event, streaming live from NASA's Kennedy Space Center Visitor Complex in Central Florida. On the screen is the University of Alabama team getting the robot into our competition arena and preparing for their first competition run of 2 runs this week. We competed yesterday, we will compete today, and we will compete tomorrow. 3 full days of competition runs in order to get the 10 finalist teams who competed at the University of Central Florida last week through 2 competition runs. It takes us 3 days to get 10 teams 2 runs. While you can see Alabama students putting up some visual markers in the arena that their robot will be using to perform some automated calculations, some automated tasks. Some of their teammates are also in our mission control room setting up the computers that will be monitoring and controlling that robot. The students who are monitoring and controlling this robot are nowhere near the actual robot. They are in a remote location, and the data that they receive from their robot is displayed on their screens, and the commands that they send to the robot come from this control room. And so what we're doing with this competition is simulating that this robot was dropped off on the moon, and that the robot controllers are back on Earth or on a different place on the moon where they don't have visual sight of their robot. And so all of these student teams, not just the Alabama team that you see on the screen, all of these teams have the option of basically manually stick driving their robot for the entire competition, or spending some time and some effort and spending some money on some sensors, for example, and creating some level of automation or autonomy on board the robot, which would make it potentially easier on the student drivers to just basically hit an easy button, and then the robot takes over from there. I talked to this Alabama team earlier, and they said that they have partial autonomy, and that they will be running some of the tasks of their mission autonomously and some of their tasks of their mission manually. The mission for all of these teams, not just the Alabama team, the mission is to start out in the corner of the arena, which is what you can see on the screen right now, and they are given a random pointing orientation before they come into the arena. And so that keeps the teams from knowing exactly which direction the robot is going to be pointed when the competition starts. The end goal is to deposit as much of this fine, powdery, granulated material that they are able to deposit into the scoring zone, which is going to be on camera 3. The scoring zone is on the other side, the other corner of the arena, which you can see in this view. It's basically the rectangle between the 4 orange posts. And so you can see the robot in its starting position in the upper left, and the scoring area in the foreground. And so between the starting area and the scoring area, there is an area where the robots are allowed to dig, and that's basically behind the robot in the scoring area, or the starting area, sorry. But between the digging area and the construction zone, or the scoring area, are some obstacles. There are several rocks and there are at least 2 craters that I'm aware of that are between where the robot starts and where the robot needs to deposit material for scoring. So we're simulating to a pretty high degree of detail a pretty realistic lunar mission where a robot was dropped off on the moon and is being remotely operated or activated some automation autonomy software to find a place to dig up this fine granular material which simulates moon dust, and then transport that material through unfriendly terrain, let's call it, and then deposit that material in a spot which is simulating the robot building a berm, B-E-R-M. And if you're not familiar, that is kind of a fancy construction word that means a hill or a mound. A linear berm would basically be a mound that is long. You could also make a circular berm, and these berms and the shapes of berms are designed for various reasons. The reason that we think we might use berms on the moon someday is to protect sensitive equipment from landers that might be landing relatively nearby. And so if you basically put a berm near the landing area and then equipment someplace downstream, so to speak, of the landing area, that any exhaust plume coming from that lander that is going to kick up dust and make it fly really fast. When you put the berm between the sensitive equipment and the lander, you're basically protecting that equipment. So that is basically the point of this competition, is to simulate a realistic lunar mission. We have also, in the rules of this competition, limited the size of these robots. We've limited the mass of these robots. We also monitor the power used by these robots and use that in our scoring calculation. We also monitor the bandwidth, the communication bandwidth used between these robots and their mission control room, and use that in some of our scoring. There's a lot of variables here, and also there are a lot of different prizes that are given out. Not only do we give out prizes for how big of a berm that these student robots make, we give out overall an overall prize that takes into account a lot more variables, including the communication that's used and the bandwidth that's used, and a lot of other variables. We also give out awards for systems engineering papers that are submitted by these students. All of these teams are required to use a systems engineering design process, which is, it's a little bit technical, but it is a way for engineers to make sure they think about certain things in certain ways, and make sure they do design trade-offs and look at data before they make decisions about the design of their robot. It looks like the 10-minute setup time is now complete for University of Alabama, and now we are just waiting for the judges to go through the checklists and make sure everything is up and running. Wow, these Alabama students have a lot of screens they're looking at. 1, 2, 3, 4, 5 screens. They have chosen to not look at the NASA-supplied house videos. Both of those monitors on the left that have their backs to the students are NASA competition supplied video feeds that the students are allowed to use. Okay, the competition has started. You just saw the students with their hands up. This robot is running autonomously. When in the control room, the students basically prove to the judge that they are hands-free, and we've seen that a lot. This Alabama robot this year is a little bit flipped around from past robots that we've seen from past years' Alabama teams. This one is technically it's a trencher and not a bucket lander. It's actually dragging the material front to back or top to bottom. It has, now that it has lowered its trencher to a certain level, now it is driving backwards. So it's dragging its digger backwards, essentially kind of flipped around from past robots that we've seen from past Alabama teams. This is going to be interesting to see if this kind of inverse trencher configuration is more efficient than earlier configurations from this team. Team is still hands-off in the control room, so this is still automated. So that appeared to be an automated dig cycle. And now we're going to see if the Alabama robot makes its way over to the scoring area without the students touching their computers or their joysticks. Looks like what I suspect the robot is doing is scanning the area with a laser scanner in order to create a 3D model of the environment around it, a 3D model of the rocks, the surface basically, and the rocks and the craters, so that it can calculate a safe path over to the scoring area. And there goes the robot. Students are still hands off. What you'll often see teams do in this competition is start out their 30-minute, okay, there's definitely a rock on the right that the robot successfully avoided. Great job. So what you'll often see teams do is start out right off the bat with any automation or autonomy that they want to try. Okay, the robot is trying to turn, it looks like. I don't know if the students are noticing that one of the wheels is turning in the wrong direction. They're probably going to want to abort this. Now students don't have this particular camera view, so they may not realize what's happening. I'm looking at their body language in the control room. They definitely sat up, they all sat up in their chairs because they knew something was wrong, but they have not taken over manual control. Meanwhile, this robot is digging itself pretty deep, which is a little scary. The treads on this robot's wheels are not super wide or deep. Okay, we got hands-on keyboards now. The students have finally decided to take over. This robot is being manually driven right now, I presume, and is slowly digging itself out. So it looks like they're going to be able to recover from this and then probably just manually drive over. Just based on the screens that the students have access to, since they chose not to use any of the NASA-provided overhead views or side views, it's possible that the students still don't know that one of their wheels was going in the wrong direction. So both of those wheels, in order to make that turn, both of those wheels need to go in the same direction, which is what you're seeing now. they may have tried their autonomy again just then, and it did the same thing again. Oh, they just turned, if you go to the control room, they just turned on the NASA camera. This gives them a point deduction in order to use that camera, but I think in this case, it may be data that they really need in order to troubleshoot what's going on with their robot. They may have been really confused if the data wasn't showing that one of those wheels was going in the wrong direction. All right, so now they're very likely manually driving this robot with its first load, which was autonomous. Oh, there it goes again. Now I'm starting to wonder if even the manual mode has something configured wrong that makes that turn. Yep. I think that turn, whether it's autonomous or manual, might. No, that appears correct. So for a robot like this, which we call, in the industry, we call a skid steer robot, in order to turn in place, you have to have the right wheels both going in the same direction and the left wheels going in the opposite, in the same direction but opposite the right wheels. And that is not what we were seeing. If the two wheels on the same side of the robot are going in opposite directions, you are not going to do anything other than dig yourself down into a trench. So, but that last turn appeared to be working fine. So either the students fixed something in real time, or it only works correctly in manual mode right now. So at 22 minutes remaining, the University of Alabama team is dumping or depositing material into the scoring zone. So, and hopefully they figured out what's wrong with the robot now that they've turned on NASA's overhead camera. They did have to take a little bit of a penalty to turn on that camera, but I think in this case, they probably needed that particular data in order to understand what was going on with their robot, because it looked like they tried several times to do something that obviously wasn't working from our perspective. Okay, the robot is, okay, turning in place, and it looks like all the wheels are doing the proper thing. I suspect this is a manual drive. The right side of the robot is in a little bit of a crater, but this robot's not having any trouble getting past that. There's a little bit of a crater right there, too. If this robot is attempting to turn, but only half of the wheels are moving, that's maybe not as productive as if all four wheels were moving. There we go. "20 minutes remain for University of Alabama in their first run." I think these students are learning a lot about their robot. obviously this robot worked well last week in the qualification rounds at the University of Central Florida. So I wonder if something changed in the last few days. This is actually a little taste of real life for these students. I know in the end that they're, going to learn a lot. This is very likely, well, I don't want to say whether it's manual or automated. I don't see any hands on any keyboards or joysticks, so this may be another automated dig. What they do is they slowly plunge their digger down into the soil, and then once it's at depth, then the robot just drives straight backwards slowly. So now you can see all 4 wheels moving straight backwards. And another camera view can show, I just missed it, can show the material being deposited on board. They have a conveyor belt on board that moves slowly as the material is brought on board. There you go. There's more come on. They do one more scoop towards the end before they're done. They're basically packing as much material on board as their robot can carry. And I believe that was automated. Oh, they're digging some more. Man, they're really packing it in there. Okay, they're maximizing this load. I'm not sure if this is autonomous or not. So I keep guessing whether it's autonomous or not, but you can basically just ignore me. I don't know what I'm talking about. I'm definitely not saying anything official. I'm just guessing. We do have judges in the control room whose job it is to notate which parts of each run were operated manually and which parts were operated autonomously. But live during the broadcast, we really don't have any visibility into that. A lot of times when the students take over manual control, when they're done with their autonomous attempts and they take over manual control, a lot of times the robot will go much faster under manual control. So that kind of implies that this is autonomous right now, which makes sense. It makes sense for the Alabama team to want to try again, even though they had a problem, because this is a 30-minute run. Oh, that might be a problem. Okay, the students are seeing that, and they're not stepping in. So this is pretty obviously autonomous. It looks like that's still going to count as scoring if they dump it right there, which looks like that's going to happen. So hitting that marker is not, I don't believe is going to count against this team. It's basically where the material ends up at the end of the run that is scored. And this appears to all fall within the scoring zone. So I think these students are going to be happy with that. especially if that was done autonomously, like the dig and the movement from one side of the arena to the other and that deposit. If all three of those were done autonomously, that's going to give them a lot of autonomy points. And sometimes the autonomy points are worth giving up some amount of material in the scoring zone. Sometimes, if you do the math, sometimes it turns out that even if you end up with a smaller berm at the end of your run, sometimes it's worth sticking with autonomy just for the autonomy points. I'm sure all the students that are competing this week have done all of that math and traded off all the scenarios in order to plan their missions. With 13 minutes remaining, I suspect this Alabama team is continuing to run autonomously, even though their productivity might have ended up being higher if they'd have taken over manual control. Sometimes it's just not worth it to lose those autonomy points. This robot is going close to where it dug before, but not exactly. You can see trenches at the bottom of the screen. You can see their first trenches, and then middle, a little bit left of the screen, you can see their second trenches. And now the third set is going to go right there. I can imagine, just looking at those trenches, I can imagine that this robot does not think it's a good idea to drive near those trenches that it had earlier created. You can see a lot of resistance that robot just hit. It may have hit a rock and had to push through it and knock it out of the way. Sometimes this material can be really, really tough to dig in. That was a very short dig. I'm wondering if that was on purpose or not. I'm not sure if it's going to find another spot. Maybe it didn't like that spot, or if it's doing its transport now. It just left the digging area. You can see that orange line in the dirt. So this robot has left the allowed digging area. So I don't think it got that much on board just then. And the students do not appear to be taking over manual control. So I guess the autonomy points. Oh no, there go those wheels again. Surely the students can see that because they're looking at an overhead camera now. Yep, they're stepping in. It's unclear to me by watching the students, although the mission control judge knows, it's unclear to me whether the students just reset something on the robot in order to fix that wheel issue and we're back in autonomy, or whether they just took over manual control. Now we should see that that time, it didn't seem to me like the robot dug very much that time. So let's see how much comes out the back. A little more than I suspected, but still, that pile is quite a bit smaller than the other two piles that you can see in the foreground. We're technically just measuring the volume of the material that's deposited. We're not being picky at all about the shape, whether it makes an actual berm or not. This competition is hard enough for these students to force them to make it a certain shape. It's also easier for us to score, if all we have to do is measure the volume that's deposited. This is the first of 2 runs for University of Alabama. So whatever's going on with those wheels, they'll have an opportunity. Okay, this row is getting very close to that trench it dug earlier. That scares me a little bit. That wheel is hovering over that trench that it created earlier. I hope that doesn't cause them a problem. All right, here goes another dig. Students appear to be hands off right now. Hands off the controls. There are 6 monitors in front of these students at this moment. 5 screens that the students brought into the mission control room, and 1 screen that we are supplying, which is emulating a camera on the lander, the lunar lander. Okay, this is definitely autonomous. I saw the student hit a button and then put his hands up to prove to the judge that this was hands-free. So this appears to be an autonomous transit from the digging area into the scoring area or the construction area, and boom, the bad thing happened again. Oh, and it just corrected itself. Okay, so sometimes robots do this. I've seen this before. Sometimes the data from the wheel motor gets a little weird because the sensor that is in the wheel motor, which is called an encoder, flakes out, either because of a bad connection or because of an imprecise mounting, or it's just slipping and not doing the perfect job that it's supposed to be doing. So I'm unofficially predicting that this robot has one bad wheel motor encoder, or just a flaky electrical connection with that encoder. And the wheel encoder just basically tells the computer what position the wheel is at. So if the computer gets bad information about where the wheel is, it will send weird commands in response. Good news is that can be fixed. And by the time this Alabama team runs again, which will be tomorrow sometime, hopefully they will have time to fix the problem. Okay, students are really hands-on right now. Typing onto the command line, possibly. Troubleshooting, possibly. Trying to restart something, possibly. All 3 students are hands-on keyboards right now. And the robot does not appear to be moving. We're just under 3 minutes left in this event, which is University of Alabama's first of 2 competition runs. These students right now are focused on getting this robot to deposit its onboard material into the scoring area within the next 2 minutes and 20 seconds in order to eke out all possible score that they're able to get from this first run. But so far, the robot has stopped short of the scoring zone, which is in the middle of those 4 orange posts. So the students have less than 2 minutes to try and get control of this robot again and deposit that material between those 4 posts. The students are either waiting for something to boot up, which happens, I've seen that a lot, or they've given up. But I don't think they've given up. I think they may just be thinking, troubleshooting, or they rebooted their computer, which can take some precious time. Just think about how long your computer at home takes to boot up. And imagine if you had a countdown clock in front of you that said 2 minutes and counting, and then you rebooted your computer. That would be hard to experience. Okay, we're under a minute. 3 students still typing furiously on 3 different keyboards. But this view shows you the 3 piles that this robot was able to deposit. There we go. We got some movement. 30 seconds. Let's go, let's go, let's go. All right, that's going to count. Do it right there. All right, I think they're going to make it. Whew, that was close. Yeah, what probably happened there is they had to reboot, and whew, that was not a good time to have to reboot. 5 seconds left, and it looks like they've done it. They have emptied their conveyor belt. Let's give University of Alabama a big round of applause. Great effort, their first run. Now they're going to come back to the pit and spend the next day or so trying to fix whatever might have gone wrong there and improve their performance and their output in their second run. Looking ahead, we're going to have San Diego State University coming up next. So don't go anywhere. Keep this live feed running in the background. If you have to focus on something else, just keep us in the background. And we will be back soon in order to watch San Diego State University perform their first run with their robot. And then after that, we will have Virginia Tech and then Iowa State. All these teams so far, Alabama, San Diego, Virginia Tech, and Iowa State, are going to be performing their first of 2 competition runs this morning. So thank you for watching. Continue watching. Don't go anywhere. This is NASA Lunabotics 2026, broadcasting live from NASA's Kennedy Space Center Visitor Complex from AMF, Astronaut Memorial Foundation's facility at the Visitor Center, the Center for Space Education. Don't go anywhere. You don't want to miss a thing. You're watching Lunabotics 2026, and on the screen right now, San Diego State University's robot is being readied for its first run of 2 official competition runs this week here at Kennedy's Space Center Visitor Complex. We have 10 teams competing this week here at NASA. I don't think I ever listed the 10 teams. Let's go ahead and do that in alphabetical order. The final 10 teams, the 10 finalist teams that are competing here this week are College of DuPage, Iowa State University, Michigan Technological University, New Mexico Institute of Mining and Technology, San Diego State University, who you're seeing on the screen right now, University of Alabama, University of Illinois Chicago, University of Utah, University of Virginia, and Virginia Tech. The San Diego State University robot that's on the screen right now is being powered on by these students and checked out. All teams get 10 minutes to initialize both their robot in the arena and their command and control system in mission control. And looks like they have about 3 minutes remaining if they need to use this time. In mission control, the students get to bring in their own equipment into mission control and also select whether or not they want to see 2 different camera views that we allow teams to use. There is a point penalty, at least for the grand prize, there's a point penalty for teams who choose to use those 2 monitors that were just turned around backwards. So the San Diego State University team has obviously chosen not to use the 2 camera views of the arena that NASA offers to teams. So this team has sensors on board the robot, obviously, also cameras that give them all the information they need to perform this simulated lunar construction mission. All right, we know we're getting close because the judge has just come in to document the power reading of this robot. These power meters that most of these teams put on their robots are basically just counters that basically just continue to count up. So we basically always take a before measurement and an after measurement, and the difference between those 2 is the power used during the event. This simulated lunar mission that we put these robots through starts out in a location that you're looking at now in the corner of our arena, and then the starting pointing direction is randomized for each run at the beginning of each run, so the teams don't know which direction the robot's going to be pointing when the mission starts. But the rest of the layout of the arena is mostly known beforehand. They know the starting area is in one corner, and they know that if we go to camera 3, the construction area is in the other corner, on the opposite side of the arena. This camera is focused in on our construction area. This is the area that the robots need to deposit as much material as possible, as much simulated moon dirt as they possibly can during their 30-minute run. What's between the start area and the scoring zone here is the area that robots are allowed to dig in, and an obstacle area that the robots have to avoid rocks and avoid craters. Some robots attempt to drive over rocks, some successful and some unsuccessful. Some robots attempt to drive through the craters, some successful and some unsuccessful. And there you see the robot in motion. So our 30-minute run has started for San Diego State University. The robot is definitely in the digging area or the excavation area right now. Possibly setting up for some automated digging, maybe. It's really hard for me to know whether things are automated or not. Are they listening? I just got a thumbs up from the students in the control room. It looks like there are some signatures on the digging buckets on this robot. I presume those are the students' autographs. This is a fun little tidbit. I'm seeing maybe some troubleshooting on the keyboard in the mission control room. Okay, yep, some body language that things are working now, and digging. So this is a bucket ladder type system. You can see those buckets coming around on that conveyor belt are each dumping a little scoop of this granular material. And this bucket ladder, if we go back to 5, this bucket ladder raises and lowers in order to choose the depth that it wants to dig. All right, and this robot is driving, possibly autonomously, to the deposit zone. I presume that if a student was performing that digging operation, they would have dug more. Sometimes the autonomy operations are not as aggressive as a manual operation. Often, often an autonomous operation is not nearly as aggressive as a manual operation. All right, so this robot has deposited some material into the scoring zone. Okay, students are definitely got their hands in the air right now, so this is autonomous driving. There's a rock right there, just barely missed it. Okay, looks like the robot went to the exact same spot that it was at earlier. And the robot is probably thinking, okay, it lowered its digger. This is all probably still autonomous. Lowered it, it's still lowering. It's lowering as it digs. So it's basically digging straight down and just plunging that bucket ladder beneath the soil. And now it's raising the bucket ladder. Probably still autonomous. Oh, there's a rock right there. Looks like it missed it. Oh, there's a rock right there. Uh-oh. 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 Danger. Okay, the autonomous driving may have gotten confused, and the students may have taken over or aborted the autonomous drive attempt. I can see typing on the computer. You can see that camera's on a swivel, so it's a dual use camera. In that position, it's focused on watching the material coming on board. And then in that position, it's focused on the driving backwards. When I say backwards, I'm assuming the front of the robot is the digging side, but I could have that completely wrong. All right. We're back to digging on the San Diego State University robot. Okay, this time it's driving forward while digging, and it's getting a lot more on board. So it's possible this is a manual. Well, I don't know. It's really hard for me to tell whether something's manual or not, but we have judges in the mission control room who are keeping very close tabs on which operations are manual and which operations are autonomous. This is definitely much more productive digging than we saw earlier. So either their autonomy software is really nailing it, or they've switched into manual digging. You can see the onboard conveyor belt is moving away from the deposition side in order to make room. All right, I think this robot is satisfied with its onboard load. Slipping, a lot of slipping right there. This robot these robot wheels are digging some holes that are looking a little scary to me. Okay, got past that. So this robot is really heavy right now because it's got all this material on board, and this stuff is not light. So the turning operations of this robot, when it's fully loaded, are a little bit of a challenge, but it made it into the scoring area. Ooh, that's a lot. And there's more. This robot holds a lot of material. I can see why it had some trouble transporting. That was a lot of material. This is heavy stuff too. If I had to guess, I would guess that was manual driving, but Only the judges know for sure. Got a really good angle of these this bucket drum system depositing material on board. That's a lot. They got to be happy with that. Looks like their hopper is still only about halfway full. Their onboard conveyor belt kicking up a little bit of dust there. Yeah, these scoops as they come around the top, they're all full, overflowing even. So this robot is being highly productive right now. This team has plenty of time to do this back and forth cycle several more times. Looks like they're done with this dig cycle and are heading over to the scoring zone. Let's see if they can make this corner a little easier this time. Yeah, that was a lot better. They didn't get stuck that time. I mean, technically they didn't get stuck earlier. They just worried me a lot when they started sinking down. All right, this is a lot of scoring material. 2 very large piles have been deposited with 17, almost 18 minutes remaining. Things are looking up. Things are looking good for San Diego State University. Students have got to be feeling good right now by seeing that kind of production out of their robot that they spent all academic year designing, building, and testing, and now competing here at NASA as one of the top 10 finalist teams in NASA's 2026 Lunabotics competition. This is a strong robot. You saw just a second ago how it was really pushing in hard, and the whole robot was fighting against those digging forces. I talked to the students earlier in the hallway, and they said that their robot is, quote unquote, a monster. They have maximized the weight. They've hit basically the maximum weight that's allowed in this competition, the maximum volume, maximum size. They have purposely hit and made this robot as big, as large, as heavy as they could in order to maximize their throughput and to maximize the intensity. Hopefully, their expectation is to maximize their score. The students told me that they are all rookies. The team has been here, the San Diego State University team by name has been here before, but all the students on this team change every single year because it is a senior design project, and so every year the previous team members graduate and go away, and a whole new team comes along each year. It's impressive what this team has done without any prior experience. All right, this is going to be their third trip with 14.5 minutes remaining in this run. The first of 2 competition runs for San Diego State University. You can see that robot, as heavy as, when it's fully loaded, is pretty heavy. You can see those wheels kind of really working hard, and they're you know, pushing into the soil. And this team has to be a little careful with their turns, because when it's fully loaded, this robot did earlier show that when fully loaded, that's a potential for sinking in. But ever since then, we've seen pretty good progress from this team and from this robot. Here's a different angle of the digging cycle. You can see the tracks and some of the trenches that were left behind from earlier digging. In the upper right of this particular view, you can see the mound, the pile of material that the San Diego State University robot has deposited into the scoring zone. And with 13 minutes remaining, still a lot of time to make that pile much, much larger. The robot, I was just going to say, hasn't moved in a while, but here it comes again. Back for more. So they're backing up to the kind of the edge and then driving forward while they dig. This bucket ladder system is digging material away from the front of the robot. And so the robot drives forward into that material, which is basically the opposite of the action that the Alabama robot was designed to do that we saw earlier. Another thing you might have noticed, just for fun, comparing this San Diego State robot to the Alabama robot we saw earlier, the Alabama robot was designed with 2 separate digging conveyors, and the San Diego State robot has 1 large, wide digging conveyor. It's really pushing in hard there. You can see the buckets kind of get slowed down as the wheels push. These wheels are really strong on this robot. Matter of fact, I hope they didn't hurt something or damage something just then. It's been a while since I've seen the buckets rotate. It's going up and down. Okay, that's moving again. It scared me for a second. Oh, there is something there. When the belt comes around, you'll see something. Looks like the belt is starting to do something weird there. Okay, now they're pushing again, pushing again. They're pushing just enough, not pushing too hard. It looks like every single one of these buckets is overflowing when it comes around. This is a strong robot, folks, and that's on purpose. They made it as big and heavy and as strong as they could. I hope they don't have one part of the robot that's so strong that it breaks another part of the robot. That's the second time the belt has stopped while they were pushing with the wheels, which makes me a little nervous. Sometimes when something breaks, it there we're going again. Sometimes when something looks like it breaks, it really is broken because something mechanical, something physical has actually broken. But sometimes when a robot stops or a part of a robot stops, it's just tripped a circuit breaker, so to speak. And most of these students will immediately see that on their displays, and basically be able to reset that circuit breaker that has tripped. That's a pretty common thing with a system like this. This may be the biggest load we've seen on this robot today. You can see its wheels are sinking in as it drives. No, I think they're going to attempt a 3-point turn here rather than just kind of spin in place, because the weight of this robot when it's fully loaded is it's a little risky to try and turn in place. Yeah, now it's going backwards. You can tell because now they're going to go forwards. You can tell which way they're going to drive this robot, because that camera in the back of the robot will swivel. Now they're going forwards. And then you'll see the camera swivel. Now they're going backwards. So I predicted a 3-point turn, and it turned into more like a 8 or 9-point turn, but that's fine. They'll get there. Hopefully. Oh man, that is really scary. That soil right there is very loose, so now it's kind of fluffy. And if the soil next to it that is not being trenched out, basically, which is under the robot right now, is not fluffy, it's still hard. And if this robot gets its wheels into light and fluffy stuff, but it gets its chassis kind of high-centered on some hard stuff, that would not be a fun place for a robot to be situated. Oh, I hate to see it getting deeper. All right, these students are obviously manually driving this robot and trying to get it from a quicksand situation. So possibly just very, very light, gentle movements may get this team out of this hole. There, okay, if they go in that direction, they can get out of it. So there's some hope there. Now they'll be able to come at it from a different angle. Ooh, there's a hole right there. That's from one of those trenches that they dug earlier. Now if they come at it from a different angle and not get their wheels into that really loose stuff, they may be okay. Again, this robot is very, very heavy right now. All right, looks like they got past it. Whew. What a relief. With 6 minutes left, San Diego State is about to deposit more material into the scoring zone. If they're not careful, that spot right there might get fluffy. 5.5 minutes remaining. how many more cycles are they going to be able to do in that time? They could do 2 if things go well. I wonder what's going on right now. Maybe they're setting up an autonomous deposit to gain some autonomy points. Under 5 minutes left. That's a lot. That's a lot of material. All right, here we go. 4.5 minutes. How much can you get in 4.5 minutes? Are they going to do one really, really big load and try and max it out for their final cycle? Or are they going to try and push it and try and get 2 smaller loads in? I don't know. Time is running short. And there's a rock right there. I don't know if this robot sees that. Our overhead camera can see rocks right there. I'm not sure if the students, since they've turned off our overhead cameras, I'm not sure that the students or the robot, if it's in autonomous mode, is seeing those rocks. Coming down to the 3-minute remaining mark. Is there still enough time to get 1 more cycle in? If they take over manual control, they might be able to drive more aggressively. Okay, students, hands on keyboards. Students appear to be troubleshooting the issue. Looking at data on the screen, typing on the keyboard. Okay, the robot's moving again. Honestly, though, there's a lot of material in the scoring position right now. It looks like one of the front wheels, front being to the right, is not really driving right now. Just kind of dragging. They may have lost some motoring capability in the last few minutes of this run. Yeah, I think the students are calling it. They know what has failed, and apparently they do not have a way to recover from what has failed. So rather than keep trying and potentially cause more damage, it looks like they've told the judge that they're gonna go ahead and call it done. Yeah, we see the timer has now stopped. All right, let's give San Diego State University a big round of applause. Look at the pile of simulated lunar moon dirt that they have deposited into the scoring zone. Great job. And whatever the issues were that they were having, they're going to get a chance to fix those issues and come back with a strong second run later on Thursday. So looking ahead, We will have Virginia Tech coming up next, and then Iowa State after them. Each run is roughly an hour apart. What time each run starts is kind of up to fate. It takes us a certain amount of time to prepare the arena and reset the arena and get it ready for the next team. It takes a certain amount of time for the prior team to safely and carefully remove their robot and clean it up and get it back to their pit. But don't disappear, don't turn off this live stream, because you don't want to miss Virginia Tech running their robot next in NASA's 2026 Lunabotics competition. Streaming live all day today, all day tomorrow. And if you missed yesterday, you can go back and watch that one from yesterday's live stream. 3 days here, broadcasting live from NASA's Kennedy Space Center Visitor Complex. Thank you for watching, and please continue to watch Virginia Tech coming up next.
Each year, the search for minerals leads miners deeper into uninviting lands, far from civilization, where not only strength, but ingenuity is required to pull ore from the earth. With groundbreaking advances in technology, Caterpillar is helping its customers overcome that challenge and changing the future of mining.
It was a complex environment. Nobody'd done this before.
I got told on a daily basis, you can't do this with big haul trucks. It's not going to work.
Good mining is about the consistency that happens shift after shift, day after day, hour after hour.
Customers have million-dollar assets that are not being utilized, and that's costing them money.
Improve productivity, improve safety.
Show people that it would really work in a real mining environment.
We're actually making this happen.
This is completely different than anything we've ever done before.
We have the world believing that this is the technology for the future.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
You're watching NASA's 2026 Lunabotics competition. On the screen, Virginia Tech's students have placed their robot into the arena and are preparing it for their first run. We have 10 teams competing here this week at NASA's Kennedy Space Center Visitor Complex, and each team gets 2 runs. So Virginia Tech is about to start their first run in about 5 minutes or so. After that, we will break for lunch because it's going to be 12:30, give or take. Well, it would be after 12. So that would be an appropriate time to break for lunch. For those in the room, when we break for lunch today, which will be after this run, we will be having a mini award ceremony on the stage at the far end of the room. We will be giving away systems engineering awards today during our lunch break. That is after Virginia Tech's run, which is about to start in 4 minutes. Actually, I was right the first time. It's probably going to be close to 12:30 when we break for lunch and have the award ceremony. After we return from lunch, we will give Iowa State an opportunity to have their first run, and then all of the runs after that will be a repeat of all 10 teams. We'll start with DuPage, give them their second run, University of Virginia, University of Utah. That may end our day, or we may, if we're lucky and have time, we may also get U of I Chicago in today. Schedule is flexible. We thank you all for your flexibility. Looks like the Virginia Tech students are leaving the arena, implying that they're happy with the robot. Everything is working. They've tested everything. Now the students in the control room are making decisions about which cameras they are going to be using, which cameras they will not be using. NASA has 2 cameras that we optionally will provide to these student teams. If they choose to use our one or both of our 2 cameras, there is a penalty applied, at least for as far as scoring goes, for the overall award. Looks like the students in Mission Control Room from Virginia Tech have chosen to use one of our supplied overhead cameras, the one that is stationary and can see the entire arena from overhead. They've chosen not to use the second camera, which is a pan tilt zoom camera that those students can control. It should be noted that the students in Mission Control are in a completely different part of the building than their robot. They're unable to see the robot with their own eyes. They are only able to see data, video from our camera that I mentioned earlier, and then the students, you can see, have a laptop in front of them, which is showing live data from their robot and several camera views, it looks like, onboard camera views from the robot. This Virginia Tech team told me earlier that they have implemented 2 different forms of autonomy, digging autonomy and dumping autonomy. So we will probably see, we will likely see this Virginia Tech robot dig without the students touching their controls, and also deposit the material or dump material without touching their controls. All right, now Virginia Tech is going to get 30 minutes in order to perform their mission. Their mission is to dig in the digging area, which is basically the entire half of the arena that the robot is in right now. They have a front bucket, and then they have an onboard hopper that dumps out the back of the onboard hopper. You may notice that this material that the robot is driving in and digging in can be light and fluffy on top, but it gets hard and it gets pretty tough once you get past an inch or so beneath the surface. This material is unique in its material properties. It naturally compacts based on the material above it. The particles are jagged in shape, which makes that compaction pretty intense. And that can make it pretty hard to dig in, and this is on purpose. This material is purposely designed to simulate moon dust, lunar soil, which is not easy to dig in, it turns out. So in other words, you can't send just kind of a wimpy kind of robot. It has to be really rugged, really tough, really strong in order to dig on the moon. The purpose of this competition is, this is a construction competition. Digging is step one, but the actual scoring of this competition involves the robot depositing this granular material, this moon dust, simulated moon dust, into the scoring zone, essentially creating a berm, a BERM, which is construction speak for a pile of dirt, essentially. And a pile of dirt on the moon could have several uses. The use that we are kind of focusing this event on is using a berm to protect sensitive equipment from some moon lander that might be landing in the vicinity. All right, this Virginia Tech robot is heading to the scoring zone for its first. Oh, okay, I was gonna say, don't unload it right there. You can see the rear, the hopper is lifting up, kind of a little bit like a dump truck, and then they have a door that is now gonna open, very similar to some dump trucks. You can see how sticky this material is. It doesn't necessarily want to flow even as high as even at that high angle. Looks like the robot shook back and forth in order to force that material out of the hopper. This Virginia Tech team chose a rubber tracked system. I got scared there for a second because the robot stopped moving. They chose a rubber tracked system for the robot. It seems to be working well. If you do the math, it might show that a rubber tracked system like you're seeing on the screen now keeps more surface area in contact with the lunar surface, which could tell you that that is the right answer. But there isn't one single right answer. Oh gosh, sorry. There isn't one single right answer for this problem. There are downsides to tracked systems like the one you're seeing competing right now. One of the downsides is dust and rock kind of jamming up the works of a tracked system with cogs. So far we haven't seen any issues with this robot's track system. So it's possible that the students have just designed it really well in order to keep rocks and dirt out of the way from areas that could be troublesome. I believe what happened there was the students were setting up for an autonomous deposit, and so it's possible this. Yeah, I see hands way up in the air from the students in mission control, giving the judge an obvious indication that they were running autonomously during that dump operation. They appear to be stick driving the robot back to the digging area. I didn't notice any obvious indication that the digging was autonomous, so this may be manual digging. Each team gets to decide how much risk they want to take in each run. This is the first run for this Virginia Tech team. They may want to take a little less risk in their first run. Exactly what risk they're willing to take and not take is different for each team. Is it more risky to run autonomously, which tends to, in a lot of cases, operate more carefully, more slowly? But also might give you a lot less productivity? Or is it riskier to drive manually and potentially do something wrong and potentially break something? So many variables, so many options for these students to choose from. You saw how hard the robot had to work just then for that little scoop's worth. This robot is now digging in an area where the the granular material is quite compact and just not wanting to be dug up. It's quite hard once you get a few inches down. All right, they're going for another deposit. They must deposit the material inside the rectangle formed by those 4 posts, because outside of that rectangle, it will not be scanned, it will not be scored. In order to score the material that has been delivered, we are using a 3D scanning system that uses laser light to scan a surface and to build a detailed 3D map of that surface. When they lift up their dump bed like that, when they're not actually dumping, what they're doing is trying to move the material backwards towards the back of the robot and make more room at the front of the dump bed. Ooh, that was a lot. All right, they're full. We've noticed today, that some robots have a little bit of trouble making that turn that this robot just made in order to line up with the deposit area. Oh, that thing goes straight up and down. Why isn't the material flowing out? Did the students realize that that not much material came out just then? Oh, I was saying some robots have an easier time and some robots have a tougher time making that turn. Oh yeah, they're into some really hard stuff right there. They're only getting little bites each time. Going pretty deep. So impressively deep, getting into the hard stuff. This robot, however, seems to be making that turn without any issues. This rubber tracked system does not appear to be digging in and burying the robot during any of these turning motions. This is quite a load on board. Let's see how much of that load they are able to deposit and empty their hopper. This is probably the heaviest this robot's been so far. This material is quite heavy. You can see they're shaking their robot. So the door is open. The material is just bridging and not, oh, there's a rock. So that rock may have kind of been jamming up the works and keeping material from coming out. There's still quite a bit of material on board. So this granular material, it doesn't always flow out of an onboard hopper. Some of that depends on the geometry. This material is, I mentioned, it resists your digging forces and it compacts. Most of these particles are jagged in shape, and that kind of helps the particles lock together and compress and lock together. That can make it hard to dig and hard to move through small spaces. So I'm not sure how wide their rear door is opening, but if it doesn't open wide enough, the material may just not flow very well out of that opening. That may be what we're seeing here. We're halfway through this 30-minute run for Virginia Tech. All right, let's get this thing emptied. It doesn't count if it stays in the robot. You can see how slow that material is to move. The students are shaking the robot, so, or maybe that's part of the automated software. Only the judges in mission control know for sure and are making note about which operations are being controlled manually by the students and which operations are fully autonomous. This onboard hopper appears to be filling up, which means the robot's getting heavier and heavier. This is going to cause a lot more, this is going to add some risk. The heavier this robot gets, the more risk there is of something breaking. This material is quite heavy. Also, the more material stays on board, the less points this team's going to end up getting. So they really need to try and empty this hopper if they can. Okay, it all just came out just then. Completely empty right there. The students got to feel good about that, these Virginia Tech students. They still have 11 minutes left, so still plenty of time to get some more material moved over into the scoring position. These Virginia Tech students don't appear to be super picky about where they dig. They're just kind of spreading out their digging and just kind of rotating as they go and just taking bites in a circular pattern. If you're curious, if this robot does pick up one of those rocks in front of it and end up somehow getting it deposited into the scoring zone, it will definitely count. We will measure the volume of that rock, and it will count towards the volume of the berm. So yes, rocks do count. This team may not want to try that though, because that rock may not slide out the back of this robot. There, they emptied again. Okay, now things are going our way. We're under 9 minutes now. So based on what we just saw, they should be able to do that a couple more times. Get a couple more full loads deposited into the scoring zone. This team appears to be getting busy, digging a little bit more aggressively than we saw earlier. Probably trying to make sure they get 2 cycles in before they run out of time. That was a good scoop right there. You can see how tough this material is when they go deep. Yeah, that was an aggressive dig cycle just then. No, they're gonna have to turn the robot around because it needs to back in to the scoring position. They're gonna lose some valuable time turning the robot around. But here they come into scoring position. Uh-oh. It looked like the left side track was turning and the other side was not. Okay, it's going forwards. Okay, now it's going backward. Oh, it's hitting something right there. There may be a rock or something in their right side track. Okay, it's fixed. That's one of the downsides of a tracked vehicle, especially in a very dirty environment. Rocks and gravel, dust and dirt. jamming up the works. All right, here we go. They still have 5.5 minutes. Should be enough time to do one more dig, travel, dump cycle. They got to lift their thing all the way up and shake the robot a bit sometimes before it finally all comes out. Nice. Okay. 5 minutes. That's enough time to do at least one more, right? They could probably do 2 quick, non-aggressive cycles or 1 very aggressive, very heavy load. Oh no, now the other track stopped working. So now the left side is not working. It's going backwards. It's going forwards. It's not going forwards. It's going back. It's going. Must be something jamming up the works somewhere. This is the opposite track than just a minute ago. Another possibility is that it is not a rock. It seems to be stopping in the exact same spot every time. Another possibility is that this is not a rock. This is a control system issue, a motor issue, a motor feedback, a motor sensor problem. Meanwhile, the clock is ticking. We have less than 4 minutes to try and get one more. To try and get one more cycle in. You can see the students are driving a little more aggressively now, trying to break loose whatever the problem is. That one track doesn't seem to be going in either direction now. It seems to have gotten worse just in the last minute. Three minutes now. Oh, it kind of started working there for a second. It's hitting something hard there, though. One possibility is that it's not a rock, that it's actually part of the robot that it's hitting. It's one part of the robot is hitting another part of the robot. That is always a possibility. These robots are getting run through the ringer. They're getting beat up in this competition. And sometimes things twist, bend. Sometimes things fall off. We've seen that several times. I don't wish that on anybody. But there are a lot of different possibilities of what could be happening with this robot right now. All right, I'm looking at the body language. I think the students have given up, which makes sense. They only have 2 minutes left, and they don't necessarily want to add any more damage to whatever has happened to this robot, because they want to be able to bring this robot back to their pit and work on it and fix it and get it in better shape than it already was. And come back strong for their second run. That's what we hope for this team from Virginia Tech. Let's give Virginia Tech a big round of applause. They were able to deposit a lot of material into the scoring zone before they ran into this problem. All right, it is a little bit after 12. Give us a few minutes. This is for folks both online and in the room. We are going to have a mini award ceremony. We're going to give out systems engineering awards. So it will take us a few minutes to prepare for that. So for those in the room, come on down to the stage end. And for those online, stick around, and we will have our little mini Systems Engineering Award ceremony here momentarily. Hello there. We are about to start a mini awards ceremony during lunch on this end of the building, so come on down and join us. Lunabotics has long been recognized as the premier systems engineering competition for colleges and universities. As you know, a paper describing your systems engineering experience is required for Lunabotics. And now it is time to present the awards for the best systems engineering papers. I would like to introduce the lead Lunabotics systems engineering judge, Jeanette Stecklin, to present systems engineering paper awards. Jeanette Stecklin.
Super. So, Lunabotics is the longest running and for many years the only full life cycle system engineering competition in the world, with college and university teams demonstrating their systems engineering prowess, competing with their designs in the arena. This year, across the board, we saw the system engineering papers that identify the performance of system engineering you did on your project, that execution to rival the system engineering performed at some of the best companies in the world. So judging the system engineering paper this year was the hardest ever. Hard because so many papers were so good, and it was really tough to choose the best among the best. My paper, judges loved the pain. As Eric Reiner mentioned at the closing ceremonies at UCF this year, many construction records were broken this year, and some dramatically broken. We saw the same things with our system engineering papers. For the SEP semifinalist round, the threshold scores to get in the semifinalist round were the highest ever. I think 5 points above the scores required several years ago. We had 23 semifinalists, we had 6 finalists, and you know we have 3 awards. But let me step back. 9 of the construction finalists that were actually announced at UCF to compete here at KSC were in our SEP semifinalists. 5 of them were in our SEP finals. And we have seen that as the system engineering paper performance for a team grows over the years, their performance grows. Sometimes that may lag a couple years, but we usually see that happen. So you might think we're only talking about teams that are grizzled Lunabotics veterans, teams that have been competing here for a decade or more. Not the case. We had several teams that did amazing system engineering in their very first year of this competition. So I will present 2 NOVA Awards this year for stellar systems engineering performance for our first year school. The judges had this to say about the first team to receive a NOVA Award this year. They were awarded bonus points for exceptional documentation of how reviewer feedback directly influenced technical design and schedule adaptations. The allocation of masses in mechanical requirements is great. Excellent discussion and allocation of TPMs. Our first SE NOVA Award for 2026 goes to Northwestern University. We know they couldn't make it with us this year. Northwestern, they did not travel to UCF either, but we do want to congratulate them. Good job, guys. For our second NOVA Award, the judges had this to say about the team. Clear discussion of the impact of the reviews on the design, along with a table of schedule changes. Reviews were described in detail, along with good feedback with the reviewers. The way the project handled the government shutdown is commendable. A clear system hierarchy is provided, showing the breakdown into major subsystems and components across the different design phases. Our second SE Nova Award goes to a small community college with a view of the mighty Rio Grande. Give it up for Laredo College. Okay, I am told there were sightings of Laredo College. Excellent. Come on down. Laredo. Everyone. All right, who's your system engineering lead? Yeah. Yes. Can you see everybody? Okay. Y'all can move up this way. Get a couple rows. You want to go over here to the middle? Okay. Thank you so much. Good job. Good job. You're welcome. All right. There was a sighting. We also, and I'm cueing Chris in a few minutes, we also like to reward Lunabotics teams who have made impressive improvements in their system engineering over their previous years. This is a school who, I think this may be their 8th year, and they just jumped up, doubling their score on their system engineering paper this year. This year, we present the SE Leaps and Bounds Award to Virginia State University. Virginia State wasn't able to make it. Their department called them back home. So I was able to present their award to them at the UCF closing ceremony. Thank you, Virginia State. Okay. We had such a great execution of system engineering this year by a team who's been with us for a while and has bounded back more than a leaps and a bounds, something that I'm calling, I have a special judges award that I'm calling the SE Rocket Award. We wanted to award what we saw a rapid acquisition of system engineering mastery from last year to this year by living the system engineering process and realizing it and telling us about it in their paper. The judges had this to say about their system engineering execution. Great job with the competition strategy diagram. The interaction between autonomy and manual control is very clear. Extra points for having verification approach on requirements and for the clear and detailed connection of interfaces to key driving requirements. Obvious that this team learned a lot of system engineering from this year's Lunabotics experience. So the SE Rocket Award for accelerating systems engineering mastery by living the system engineering process goes to University of Illinois at Urbana-Champaign. Now I know you have to be here somewhere because we have our SE feedback session tomorrow. Yes, yes. Okay, UIUC, somebody yell if you see them and we'll stop and take their photos. Okay. System Engineering Paper Award. Yeah, the big money. And now for the top 3. This truly was the most difficult. this year. The point spreads are very small. So our third place system engineering paper team receives a $500 scholarship award. About the third place winner, the judges had this to say. The information was very well done in each SE area. They did a great job with requirements and verification plan, as well as adding a risk management section. Mature definition and execution of reviews. It was good to see the CDR being properly used as a control gate with a delta CDR needed before project progressed. Clear thinking about operation of the system with good allocation to organizational elements, as well as some thoughtful consideration of failure mode responses. OV1 and functional flow diagram to describe the overall ConOps was appreciated. The third place winner is University of Illinois, Chicago. It's a good year for Illinois. Yes. Yes. Oh, we need more. Oh, yes. Oh. Come in behind. Couple rows. All people in the back. No. Here. There we go. Can you see everyone? You got everyone?
Yes. There's some. Not those if you don't want them.
Can you see everybody? Super. Okay. Our second place winner receives a $1,000 scholarship award. About that team, the judges had this to say. Good quantitative assessment of prior performances and use of that data to set key driving requirements and key performance parameters, including the use of margin. Great job connecting the concept of operations to key performance parameters, showing how the top level requirements were decomposed through the ConOps quantitatively. Excellent discussion of interfaces, both internal and external, and how simplification of interfaces drove their final down selection of design alternatives. The second place winner is University of Virginia.
Ethan Edwards here.
There we go. Okay, I said this was our closest yet by 0.2 of a point. Now for the first place system engineering paper that receives a $2,000 scholarship award, our judges had this to say. Great job tracking TPMs through the life cycle. Awesome risk reduction with access to a representative arena. Multiple issues identified and repaired. Use of a very disciplined review process, no doubt about the reviews being control gates. Excellent delineation of how the schedule and budget were used to manage the project and affected project and design decisions. So do we get a picture with you for the first place team? Because I'm about to award it. Hold on. The use of timing analysis for the final ConOps is very advanced and really helps prepare for mission execution. Very thorough in how the specialties drove many aspects of the designs and trades. Excellent description of what happened during verification, having some verification failures with the resulting impacts to schedule and budget and design denoted. Our first place SC Paper Award goes to the University of Alabama. Who do we shout out to?
These two.
Excellent. Excellent. Everybody. Right. Can somebody help the student astronaut up the stage? There you go. Excellent. Yes. Okay.
Shout out to Bridget Noonan.
Excellent. Thank you. Thank you. Thank you very much. That concludes our ceremony. Am I turning it over? Okay. And Kurt for the rest of the day's events.
Thank you, Jeanette. All right, it is lunchtime. And then after lunch, we will have Iowa State, give them an opportunity to run their very first run. And then we will start through the cycle all over again and start some second runs, starting with DuPage, University of Virginia, University of Utah. I don't know if we'll have time, maybe University of Illinois, Chicago. There is a seminar at 2:30, correct? There's a very important seminar at 2:30 across the hall there, right, in the seminar room. It's Systems Engineering from the Basic to the Advanced Part 2. Systems Engineering, Basic to the Advanced Part 2, 2:30 p.m. Don't miss it. What time is Iowa State going to start their run? I do not know. They will run when we get everything ready and have a quick lunch break. So stay tuned to this live stream. Stay in this room. Okay, Rob Mueller has an announcement. Do not go anywhere. Rob Mueller.
Okay, congratulations to all the teams. We have an important announcement. You have done so well depositing regolith into a berm that it's killing our regolith judges. They can't shovel it back as fast as your robot can deposit it. So it's affecting our schedule because we have 15-minute turnaround time, but they can't get it all returned in 15 minutes with the shovels. So we're going to be behind schedule. It's not going to work out. So the judges team have met, and our proposed solution is to reduce the runtime from 30 minutes to 20 minutes. There's two good things about that. It's less regolith, so our judges have to shovel less regolith. So that's one appeal of that strategy. The other thing is it gets us back on schedule. So for round 2, you will get 20 minutes runtime, okay? We have to do it to stay on schedule. The other thing is in the guidebook there was a dimension of the center of the berm envelope where the berm can be built. That number has been corrected because it was to the edge of the PVC pipe and not to the edge of the wall of the bin. So we have corrected that. We're going to have corrected sketches available at the pit boss desk. So if you are doing autonomy and it affects your programming, you may want to know that number. If you're not doing autonomy, it probably won't affect you. So those are the two announcements I have. Thanks.
All right. I almost forgot. There's a seminar at 1 p.m. that I forgot to mention. It's on NASA internships. So 1 p.m. seminar on NASA internships, 2:30 p.m. seminar on systems engineering, basic to advanced part 2. Go have lunch, but don't go anywhere because you don't want to miss the rest of NASA Lunabotics Day 2. Bye, but don't go anywhere. You are watching NASA Lunabotics 2026 Robotic Construction Competition. We have just gotten back from lunch, and you're seeing Iowa State University's robot in the competition arena. The 10-minute setup timer is just about expired. This will be Iowa State University's first of 2 competition runs during this 3-day event being held at NASA's Kennedy Space Center Visitor Complex. There's a nice view of the Iowa State robot. I talked to these Iowa State students earlier, and they take great pride in the dust tolerance, the ability for the robot to keep dust out of certain parts of the robot and to minimize the lofting of dust. You can see overall this robot is covered with a red material. It's like a thin light parachute kind of material. And all of the seams are taped with an aluminum tape. The Iowa State students have chosen a tracked vehicle, a metal track vehicle, and a bucket ladder system for digging with a large onboard hopper. We should momentarily see the 30-minute timer start for the Iowa State team. I asked the Iowa State students if they thought it was an advantage or a disadvantage to go last among our 10 finalist teams. And they said, without question, they wanted to go last. Matter of fact, they checked in as late as possible, hoping that that would allow them to go last. So they were hoping and planning to go last. And they're hoping that that gives them more information I think they were mostly focused on it giving them the most time to prepare, which is a valid. Okay, those tracks seem to be spinning without any motion of the robot there for a little bit. So these tracks don't seem to be giving as much grip as maybe is necessary at this moment, at least during the turning of this robot. I asked the students how much autonomy they had. They said they were pretty close to full autonomy, but they probably weren't going to go and try a full 30-minute mission of full autonomy. They said that was too much risk, too much work. They said, and we've seen many teams do this, they said they would probably do one cycle of automated mission operations, and then after that, perform the rest of their mission manually. It's a trade-off that all teams have to make in this competition. You do get extra points for having certain portions of your mission occur in an automated fashion where the students are not actually actively controlling the robot. The trade-off, and you get a lot of points for that, the trade-off being autonomous operations can oftentimes be a lot slower and less productive than just stick driving the robot, where you can make decisions in real time and push things right up to the limit. This robot seems to be focusing its digging in this starting area, which is completely allowed. Basically, the whole entire left side of the arena is the digging area or the excavation area. So this Iowa State team appears to be distributing their digging into different spots in order to not create, there's a rock right there, in order to not, just create one giant ditch that might get in the way later. Although if they kept going, this could be a really long, continuous ditch. I do see the student in the control room pushing buttons on a joystick right now. So at least this digging portion for this cycle appears to be manual. And now they appear to be driving, maybe not. Nope, they're setting up for another dig spot. They're distributing their digging for sure. You can see their bucket ladder digging system plunging down into underneath the surface, and then they drive forward and basically dig a trench in between the tracks of the robot. This is a good angle. You can see the material becoming fluidized in front of the robot. That's kind of fun to see. This robot appears to be pretty strong. It's powering through even the tough lunar simulant to the point where it's fluidizing it in front of its excavator equipment. So this lunar soil simulant that we have in our arena is very, very fine powder of crushed volcanic rock, which is very similar to the material that completely covers the moon. Okay, they're turning the robot around, doing some 3-point, 4-point, 5-point, 8-point turns. Whatever works. And it looks like they're heading over to the scoring zone, the build zone, the construction zone. Once they deposit material into this construction zone, it will count I'm confused about where this robot dumps. Yeah, I was kind of thinking that maybe it was facing the wrong way, but I was afraid to say it out loud. Since this is the first time we've seen this robot here at our event, this robot, all 10 of the robots that are competing here at KSE did compete last week at the University of Central Florida Lunabotics qualification runs. Yet this looks a lot like an autonomous dump, autonomous deposit. It appears that the students set the robot up and then hit a button to say, go do it. Okay, that's a nice, there was a lot on board right there. That looked like a lot. when they drive away, we'll get a better picture, a better view. Okay, the student just picked up the joystick again. And they're either programming an autonomous drive or they're driving it manually. Looks like the student is driving this robot manually right now. Student is probably going to want to avoid those rocks. I should mention that the students have control over one pan tilt zoom camera similar to the camera I'm looking at right now. Students have a similar one that they can control with a joystick. So they were able to see those rocks just like we were. Sometimes students choose not to use a house-provided camera in order to gain some extra points. These Iowa State students chose to use one of our two possible cameras. They chose the pan tilt zoom camera, and they are not using the stationary camera, which gives an overall overhead view of the entire work area. When you see a robot that's being driven manually, pause like this, oftentimes the students are activating an autonomous system on board. So this, yeah, I see no hands on keyboards, no hands on joysticks. So this is a high probability that this was an autonomous dig attempt. That was very quick. The students may decide that it's not worth, yeah, the student just picked up the joystick, so they're either gonna tell it to do another autonomous dig if they want more autonomy points, or they're just gonna give up on that idea and dig manually at this point. These Iowa State students told me that they spent a lot of time and energy designing this robot to maintain dust in certain areas, keep dust away from other areas of the robot, in hopes that that would increase the reliability of their robot. And there's a special prize category in Lunabotics for teams, for the team that has done the best job in the judges' eyes of not only keeping dust out of certain sensitive parts of your robot. Look at those rocks being pushed in front of that excavator. That's crazy. Not only keeping dust away from sensitive parts that might be harmed by dust, but actually keeping dust from lofting up in the air is actually also considered by the judges. All right, looks like they're going back for some more digging. I see hands on joystick. So this looks like it might be a manual dig cycle. Looks like they're in the same track that they just dug in. So possibly did that on purpose and are just trying to go deeper into that same slot. Okay, now they're kind of going right next to the slot that they just made. Now when these tracks fall into that hole right there, which is the slot that they dug in last time, they did not blink an eye. This robot did not have any issues when its tracks went into the earlier slot. This robot has to have a lot on board right now after doing those two really long trench digs. I see student controlling this robot with the joystick right now. This is a really great view of this robot. Now they're setting up a different angle for another dig, it looks like. Plunging that digger down beneath the soil so that it is several inches down, and then driving. I was going to say driving slowly, but this robot actually drives at a pretty good clip while it's digging. They had to raise the bucket just then, the bucket ladder system, and they're lowering it again. It was kind of going downhill, so I could see that the system might have needed to be raised up back then, but now it's going uphill and probably needs to be lowered. Yep, because now they're digging in midair, which is not super productive. Do the students realize this? Hard to tell. Now they're back. They may be full, because that was a lot of digging. Or are they going back for more? They're doing a 3-point turn. It's time to get credit for all of that digging now, I think. Yep, they're heading to the scoring zone. Now, if they don't turn the robot around, if they back in, they'll save some time. Student manually driving with the joystick. They're having trouble with the right side tracks. I'm assuming that we're looking at the back of the robot when I say right side. They seem to be working again, but I think for a moment there they were stopped. Alrighty, this is good. We're halfway through their run, and they are in a really good scoring position. It's hard to see how much is on board until they deposit that material. I think something is getting caught somewhere. Now the left tracks don't seem to be. Student is going to take one more attempt at backing this thing into the scoring position. Sometimes we see tracked vehicles that just work seamlessly and don't have any issues in this very granular and rocky material, and sometimes we see tracked vehicles that appear to have some sort of issue. Okay, they made it. I guess that's true for wheeled vehicles though too. Sometimes sometimes there's a wheeled vehicle that doesn't even blink, doesn't even notice that it's traveling on some really weird, strange material, and others seem to have issues. There are a lot of variables there. The diameters of the wheels, the widths of the track, the length of the track, the size of the motors, the power of the motors, the size of the battery powering the motors. There's some, ooh, that's a lot of material right there. That's got to feel good. There was a little bit of a struggle to get that robot backed into scoring position, but they were able to dump most or all of that load into scoring position, which is in the middle of those 4 orange posts. Oh, I'm sorry. I keep forgetting I'm wearing a mic. My apologies. There's a rock right there. Some robots don't worry about rocks and just climb over them. Some robots avoid them and don't even tempt fate. And some robots have trouble with them. All right, let's dig some more. 11 minutes left for Iowa State University in their first run. After this run, I should mention, after this run, DuPage is going to get their second run, their second and final competition run. There is something interesting that happens between the end of the first runs and the beginning of the second runs. The arena gets reconfigured, and the starting zone stays in the same place. The construction zone or the scoring zone stays in the same place, but everything in between those two zones changes around. We will get rocks in different locations. We will get craters in different locations, different sizes. And so all 10 of these teams' second run will essentially look the same, but it will be different from their first run. It may be more challenging terrain. It may be easier terrain. My money's on more challenging though. Okay, that was a good dig. I love that. I love looking at the rocks that show up at the front of this robot. I wonder if that's due to the fluidization. There's a rock there. These tracks are metal, by the way, and they're pretty tough. But as opposed to rubber, if they go over a sharp rock, I do fear that there could be some damage done. I mean, I suppose a sharp enough rock could damage rubber, though. All right, Iowa State is digging again. And just like before, they're kind of randomizing their digging zones to try and spread out the area that's getting dug into, that's getting trenched. So they're basically making trenches all over the place in varying directions. I suspect that is a conscious decision that ends up making, it makes it look a little bit of a mess, but in the grand scheme of things, it kind of evens out the terrain and doesn't give you one spot that is just impassable. There's a rock there. The students must be having a little bit of an issue controlling exactly where the robot's going, a little bit of mobility issues, because they are looking at an overhead camera that they have pan, zoom, tilt control over. So I'm fairly certain they knew that rock was there, and yet the robot still hit it. So that kind of implies that there's something going on with the robot that's causing them a little bit of grief, and it's not doing exactly what they're trying to tell it to do. Now that backup move right there looked perfect to me. So that seemed to be under perfect control, but it might be in the loose soil that they're having a little bit of issue. It might also be turning where they're having a little bit of an issue. They seem to be raising their dump system. Under 6 minutes remaining for Iowa State's first run. And they're back to digging. That part of the arena is a little deep. I believe there was a crater there when we started, and they've been digging around that crater. Oop, now we're back to level digging. So it appears that this part of the arena is relatively flat, but there behind the robot where it started is a low spot, and that can affect the productivity of some of these robots. That looked like a pretty productive strip to me. Now it looks like they're going to shift the robot and maybe hit that same spot, but shift it a little bit. Occasionally it seems like one of the tracks doesn't move, and I think this is one of those cases. Could have been a rock stuck in the system. It just stopped right there. It stopped hard right there, but it goes forward. But when they back up, it stops right there in that same spot. We have seen this before with another tracked competitor. Under 3 minutes remain. So hopefully Iowa State can get unstuck, whatever is happening with their track, and deposit this load before their 30-minute timer runs out. In this overhead view, you can see the track on the left is, oh, now they're both working. Never mind. Whatever was wrong just went right. This should give them just enough time to deposit this load into scoring position. With 1.5 minutes left. Oh, sometimes they have trouble making this curve though. In the same spot. All right, I'm getting nervous. You got to get this thing unloaded if you want it to score. We're under a minute. This is going to be a real shame if they can't unload whatever they have on board the robot before the timer runs out. They've done all this work to get that material on board. 20 seconds. Ten seconds. I don't think there's enough time. Let's give Iowa State University a big round of applause. Quite an effort. If we pop over to camera 1 for just a minute, even though it's not a great view of the robot, this camera gives us a pretty reasonable side view of the scoring zone, which is in the upper right of the screen. And you can see the mound that this Iowa State University has deposited into the scoring zone in between those 4 orange sticks. So even though this Iowa State University team obviously had some issues with their mobility system, their tracks, or their control system, I still think they're going to be pleased with the berm size that they created in their first run, and assuming that they understand what happened or are able to troubleshoot and figure out what happened wrong in that run, hopefully they'll be able to fix that and come back strong and have a really strong second run. All right. What's going to happen next is our judges are going to reset the arena and get ready for the first team to perform their second run. As I mentioned earlier, the obstacle zone, the rocks and craters are going to be distributed, laid out in a different pattern. That has been a secret to all of these teams up until they basically find out when it happens. And so that may take a few minutes, so be patient. Don't go anywhere, because you don't want to miss the start of the second half of Lunabotics 2026, where we start running all of these 10 teams for their second run. And if you missed the announcement earlier by our chief judge, Rob Mueller, in the interest of, this is a problem that's actually not a bad problem to have. at least for us running this competition. The problem we have is that these teams are depositing so much material, they're digging up so much material, it's taking our arena judges a lot longer to reset between runs than we had anticipated and that we had planned. And so we've had to make the tough decision to reduce the time of all of the second runs for these 10 teams from 30 minutes to 20-minute runs, and that's going to speed things up a little bit for the second half of Lunabotics. So as soon as we reset the arena and get it all set up and ready for the first of 10 second runs, we will see DuPage have their second run. Then we will see University of Virginia have their second run. And assuming we don't run out of time, hopefully we will see University of Utah have their second run. And who knows? Depending on what time it is, we might even see University of Illinois Chicago. So that's what's coming up here at NASA's Lunabotics 2026 collegiate competition. And don't go anywhere, because you do not want to miss all of these second runs, which are about to start in just a little bit. So don't go anywhere. You don't want to miss it.
This competition for NASA is part of their Centennial Challenge program. What we're going to see this week is 2 teams who have made it to the final step be able to actually print a 1/3 scale habitat that may ultimately be used on the surface of Mars.
The kind of materials they have selected to build these habitats are materials that will represent what could be found on the surface of the moon or on the surface of Mars, perhaps.
It's really a form of incentivized R&D where NASA provides prize money to pursue innovation that meets, again, NASA's mission objectives of space exploration, but also can provide real value for here terrestrially. A great example is the work we did with NASA at Johnson Space Center, where we worked on remote control and creating an operator center so he can drive a machine, could be many miles away. And that operator center actually moved forward, and you can see it today in Caterpillar's command for dozing product, for example. And so certainly this technology that we're looking at this week has that opportunity of being a very disruptive, transformational technology for even the construction industry here on Earth.
NASA was interested in working with Caterpillar because they have experience, of course, in construction. And if we want to build habitats, we go to the experts, right? So we are reaching out to the people that have done this for years and years to help us make sure that what we're doing makes sense.
I think this competition, is a public example of what we do here at Caterpillar every day. There may be a public image of Caterpillar and we certainly are a manufacturer of heavy equipment, but really we are a technology company, and we provide that technology through large equipment like you see behind me here. We provide that technology through large equipment and services that we provide. I believe that's who Caterpillar really is.
"250 years ago, 13 colonies laid the foundation for the greatest and most enduring democracy in the history of the world. One driven by courage, faith, and freedom. From that moment, we became a nation defined not by where we stood, but by how far we were willing to go. We conquered vast frontiers, invented tools that shaped a modern world. We found light in the dark, and we rose from the earth. Faster, higher, farther. We pushed beyond the sky and into the unknown. We carried our courage into the cosmos, and we planted the American flag on the moon, the defining achievement of American superiority in space. Today, our curiosity stretches farther than ever. American robots search ancient rivers on Mars. New telescopes unfold to glimpse the first stars. And a new generation prepares to return to the moon, this time to stay. For 250 years, America has carried the light of humanity forward. But American exceptionalism isn't inherited, it's earned. Our greatness comes not only from what we've done, but what we're still determined to discover. Because in every era, across every horizon, America is at its best when it's reaching for something greater. America celebrates 250 years, and we are leading the world into the future.
I will go on record to say that that was quicker than I thought it was going to be. The arena crew has reset the arena and changed the rocket crater configuration per the chief judge's direction in record time. And now College of DuPage has finished their 10-minute setup time. They have their robot in the arena ready to go. They have their students in the Mission Control Center ready to go. And momentarily, we should see a 20-minute timer versus the 30-minute timer that all of the teams got during their first run. So all of these teams now, here it comes, all of these teams now are going to get 20 minutes to perform their second run. And here we go, College of DuPage. If you remember, or if you watched this, yesterday this team from DuPage, oh, their students are hands off. They're all raising their hands way over their heads. This is fully autonomous right now. That was a dig. That was an autonomous dig. And now hands are going on a joystick. So they got looks like they got the points for an autonomous dig. Now they're driving their robot to the scoring zone. If you watched this team yesterday, boy, you got a treat. This robot ended up, and by the way, this is a much smaller robot than the ones we were just watching. This robot is at least half the size of some of those robots that just competed, if not smaller. But what we saw yesterday was this tiny little robot created the biggest berm we have ever seen in the history of Lunabotics yesterday. Okay, it looks like the students are setting up for an autonomous dump. Their hands are way, way up in the air. So this is a fully autonomous dump. And a little bit came out. So the autonomous dig got a little bit on board. The autonomous dump got a little bit in the scoring position. What you'll likely see is for a large part of the remaining 18 minutes, you'll likely see these students just stick drive this robot and be as aggressive as you are going to see in the competition, I suspect. They're going to try and maximize each load by digging as hard as they can and driving as fast as they can into scoring position. And it's going to be fun for me to try and keep up with the cameras as fast as this robot is. And here comes I have no idea if this is autonomous or not. I suspect not. A lot of teams, once they get the autonomy points that they know they can do, they will spend the rest of the event just stick driving the robot. We've noticed that quite a bit from several different teams. They have calculated that that is going to be the way to maximize their points in this competition. You see how deeply that bucket pushes into the ground, enough to raise the front of this robot's tracks. And the robot pushes really hard. This robot does have an onboard vibration motor that vibrates the center-mounted bucket during the digging operation. It also vibrates the center-mounted bucket during the deposition, the offloading the dumping, which you're about to see. And that will fluidize, that vibration motor will fluidize this material and help it flow out. Can you imagine if they hadn't turned on that vibration motor, how slowly or not at all that material might have come out? All right, so they've had 3 trips in 4.5 minutes. So do the math. That should be how many trips they end up doing in 20 minutes. And we should kind of get a sense of how big the pile is that this team is going to end up with, how big of a berm. Without that onboard vibration motor, this small robot would be getting much smaller loads each time. The material just really pushes back on you. It really restricts your digging forces. It's weird because it got really quiet in here. Everybody's just focused on watching College of DuPage right now. 14 minutes remain. I think all the other teams are holding their breath, watching this team just perform so well. I was wrong earlier when I predicted that the obstacle area was going to be more difficult. This appears to be almost just a simple arc shaped path between the digging area and the construction area or the scoring zone. Twelve and a half minutes remain. This is it. This is the second run for this team. So whatever they get here is going to be, that's going to be it for this competition for DuPage. So they've got to really be aggressive here and just go for it. They got to drive it like they stole it, as you say. Each one of these loads is really impressive. 12 minutes remain, and you can see they've got quite a berm going here. They're changing their drop-off spot every time in order to spread out the berm, to spread out the scoring material in the scoring zone. They're digging in a slightly different spot each time, it looks like. They don't want to make too deep of a trench in one spot. Doesn't look like they got quite as much that trip. But time is of the essence. Second guessing yourself and going back for more could cost valuable time. Students are making real-time decisions here with a clock that is running down very quickly. One thing about this robot is, at least while it's digging, it seems like it's impossible for it to sink in and get stuck. It continues, even though it doesn't have a ton of ground clearance, its tracks are wide enough and long enough, and even when those tracks slip, the robot just continues to push forward and not sink into the soil. I mean, the fact that there's a vibrating bucket in the middle of those tracks could have a lot to do with that. Picking the spot to dig is going to be pretty key in how quickly they're able to get their bucket full. 8.5 minutes remain. That may have not have been the best spot. That didn't seem like that was very much on board just then. They're going to go back. They're going to go to another spot now, it looks like. You can see the bucket coming up even while they're continuing to press forward. They don't seem to have a ton in that load. Many of their other trips had much more material than that. 7.5 minutes remain for College of DuPage. This is their final run this week. What does this team need to do to fill up this bucket right now? They need to start back further. I'm liking what I'm seeing right there. Look at it piling up in the back of the bucket right there. Now they're lifting up a little bit, but they're still pushing in. Yeah, that's a good load right there. This College of DuPage team is made up of only 12 students, one of our smallest teams that ended up in the top 10. And when I talked to them yesterday, they said they are a very young team, mostly freshmen, and just a few sophomores. So this very young team has had some fresh new ideas, they claimed, and didn't have any veteran teammates to push back on their new ideas. And they said that was, they thought that was an advantage that their team had. It's amazing that such a young group of college students have made such a productive robot. That feels like a healthy load right there. This DuPage team told me that they chose to manufacture things on their robot that they could have actually purchased. They said they made that conscious decision to do the extra work in order to give this experience, this manufacturing experience, to their team members. We're under 4.5 minutes in College of DuPage's competition. After this, the students of DuPage are just going to be able to sit back, relax, know that they've done a great job here this year, and just watch the competition, watch the rest of the field try and beat them in berm size. Under 4 minutes. Should be able to get a couple more of these cycles in, I believe, in 3 minutes. Or they could really focus and try and maximize maximize the load in one last loop. They're digging early. Digging in a new spot, a little bit of risk there. That's a fairly soft area, so they should be able to get a lot right there, even by going a little shallow. They're pretty deep right now, but I've noticed they've been raising their bucket a little bit as they dig. Oh, it looks like they're gonna go for two cycles. Actually, that was quick enough. They could maybe. Wow, there's a lot in that load right there. For as quickly as they just did that, that's an impressive bucket full. They have time to do one more, right? They can't do 2 in 2 minutes, right? It is a very fast, agile robot. Okay, they're digging right on the edge of the allowed digging area. Took about 40 seconds to start digging. I mean, 20. Took about 20 seconds to start digging. And now they've been digging for 10, 15. And they're backing up as they lift up, doing some parallel work there. And now, depending on how quickly they dump this, that's another full load. These last couple loads have been really, now they have oh wow. If they hurry, they could get another small load because they still have a minute, and that last cycle only took a minute. This is going to have to be a lighter load, though. They still need about 25 seconds in order to get back and to get dumped. I would shoot for 30 if I were them. Move, 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 move. This is going to be their last load. Hopefully they are able to dump it in the scoring position. With 20 seconds left, it looks like they're going to make it right there. They gotta be happy with that. With 10 seconds left, that's all they have time for. Let's give College of DuPage a big round of applause. What an amazing second run. They had an amazing first run. They have just really, really done some amazing work here this year at 2026 Lunabotics Finals. All right, coming up next is University of Virginia, and then after that we will have University of Utah. I do not believe we're going to have enough time today to fit in University of Illinois Chicago, sadly. So don't go anywhere because there's more Lunabotics 2026 Finals event coming up next. We are looking at the University of Virginia robot in the arena, halfway through their setup time for their second and final run. I was told that this University of Virginia robot, the drums were 3D printed in orange and navy blue, which are the University of Virginia's school colors. I was calling this purple yesterday. I apologize. You may recall that yesterday, in their first run, the University of Virginia's robot lost a wheel, one of its 4 wheels. A 3D printed wheel broke off, and the students really did an impressive job of driving their robot, using the arms of the robot in order to keep its 3 remaining wheels touching the ground, and essentially just dragged those bucket drums behind them using their 3 remaining wheels. And they did an impressive job yesterday of dealing with adversity and finding a solution rather quickly. And after they found a solution, they were able to actually deposit some more material into the scoring zone yesterday while limping on 3 wheels. It was pretty crazy. You can go back and watch the video if you missed it from yesterday's live feed. This University of Virginia team is technically their school's Mechatronics and Robotics Society. Their team members are made up of the Mechatronics and Robotics Society, otherwise known as MARS, which is appropriate because NASA is planning on sending humans to Mars to explore someday after we kind of test out and prove all of the necessary technologies for long-term planetary exploration on the moon. The Virginia students call their robot Bruno. So, you know, Bruno Mars, get it? This team does have some autonomy. They tell me they have dig autonomy, dump autonomy, and traversal autonomy. Their broken wheel is on display in mission control as a reminder or an homage to yesterday's broken robot that these students were able to not get frustrated, not give up, and really make a good situation out of what could have been a disaster. So kudos to this team. This robot uses rotating bucket drum diggers, which you can see on the screen here. These rotating bucket drums, the students tell me, maintain constant contact with the digging surface, the surface that is being dug, and they claim that that is the most efficient way that they found to dig. You'll notice that they are not using plastic wheels today in their second run. They are actually using their backup set of wheels. They did bring more plastic wheels, for the record. They brought some backup plastic wheels, 3D printed plastic, and it's one of those that broke yesterday. They also brought a full set of backup metal wheels, which is what they decided to go with for their second run. All right, 20 minutes clock has started, and they're digging right there in place. Probably autonomously. I see students with their hands up. Now I'm wondering if this was if this is manual digging, because it's much more aggressive than what we just saw, which I think was autonomous. I believe the orange drums are more full than the navy blue drums. I hope that doesn't cause issues. So the back of the robot is heavier than the front of the robot right now. Hopefully that does not cause any tipping. The robot got really close to that column in the middle of our arena. I'm trying to decide if this is an autonomous traverse. It's really hard to tell based on the body language of the students. Only the judge in the mission control room knows for sure if this is autonomous or manual driving right now. Okay, I think that was manual, and now this is autonomous, because I just saw the student put the joystick down and put their hands up. So this is autonomous dumping. Oh boy. I didn't mean to laugh. That is not a fun place to be for this robot. I did sort of call it earlier though, when I noticed that the orange drums were more full than the navy blue drums. They're going to have to get rid of some of that material. Hopefully not all of it. I guess they had to dump all of it, sadly. This is a risk with, oh, there's a rock right there. All right. Virginia is going back for another load. Let's see if we get even digging front to back this time. Orange has definitely hit the ground first. Orange is a little deeper, maybe not. Maybe they're even that time. This robot does have a situation when depositing material. As soon as it empties out either the front or rear drums, the other ones are obviously much heavier and could potentially cause tipping on this robot. Ooh, they're really close to that column. Again, that's the second time they've done that, which kind of makes me wonder if that was an autonomous drive. No, I believe that was a manual drive. Okay, no, that was, I keep changing my mind. That was autonomous. Once I figured out where the joystick was in mission control, they were hands off during that drive. Which explains why they got so close to that column. I don't think a student driver would risk getting that close to that center column. All right, they didn't tip over that time, thankfully. 14 minutes remain in University of Virginia's second and final run. All right, they've got a lot of work to do in the next 14 minutes to make an appreciable sized berm. Looks like they're going back roughly to the same spot as earlier. They appear to be stick driving. Still appear to be stick driving. All right, both buckets appear to be roughly half full. This team has created see-through panels on both sides of their excavators' digging drums, which allow us to see the level of dirt inside. So all four of those drums look to me to be right at the halfway point. Not to say that they really want to have more than that. The team may consider that full, honestly. You know, they've done the engineering analysis. They know how much is safe to put in these drums. Definitely half full does not cause a tipping situation. All right, so that was a good cycle. 12 minutes remaining. See if we can do several more of those. They appear to be stick driving this robot now. They may continue for the rest of this run, just for time's sake. They may have said, that's all the autonomy points we're going to go for. Let's just go for speed and maximize production. Okay, the blue drums definitely started digging before the orange ones. That could make them more full, or the orange ones could catch up. You can see how slowly those arms raised just then, kind of implying that, boy, they're full. All right, these rotating bucket drums appear to be doing a great job of digging. These metal wheels with the large fins or grousers or tread appear to be doing a great job of driving in our simulated lunar dirt. It's just a question of productivity rate now compared to the productivity rate of other robots. We're under 10 minutes, so just past the halfway point for the second and final run of University of Virginia. Excellent. Let's go back for more now. You might notice when they dig, their wheels can and usually do come off the surface. Watch right there. They're in midair now. They are using the entire weight of this robot to push as hard as they possibly can downward while these bucket drums are rotating. This robot has no, it can apply no more force than it is applying in the downward direction during these digging operations. The only way this team could possibly apply more downward force would be to make their robot heavier artificially, because obviously it doesn't need to be heavier. They chose to make the robot this exact weight, under half the weight that is allowed by this competition. They could have made this robot super heavy if they wanted to, in order to give them more downforce, but I suspect they did the calculations and figured out how lightweight they could make this robot while still giving enough downforce to actually break through this tough material that is our lunar simulant, our moon dirt, stand-in for moon dirt. 7 minutes remaining. Even in the light and fluffy material, which is kind of where they've been digging, this University of Virginia robot does not appear to slip on its wheels, and it does not appear to dig in as we've seen some of our robots do over the past couple days. So this team has done something right regarding the mobility system, or the wheels and the motors and the gearboxes and the batteries and computers that are driving that system. So NASA, I was going to say, is going to want to study this robot, but NASA is already studying all 10 of the robots that are competing here at Lunabotics 2026. We have NASA folks that are watching online. We have NASA folks that are here in person. We have NASA folks that are going to be reviewing the footage after the fact, taking notes, possibly asking these teams questions about what they're seeing, and learning what worked and what didn't work. And NASA has every intention of learning from this competition and improving our robots, our construction robots that we are planning on sending to the moon in the next few years. So not only does this competition really benefit the students who are getting this really great experience of designing and building and testing and competing with a robot in this event, but NASA gains some really great benefits too by having all of these prototype lunar construction robots performing in front of our eyes and in front of our cameras that we're able to learn from. It's the robot, the students appear to be picking a slightly different digging spot every time, which is probably very wise of them. If they make a hole that's too deep, that might cause an issue. It might cause some high centering of this robot. Three and a half minutes left, and University of Virginia is creating a very respectable berm. It's a little hard to tell from this angle and based on the overhead lighting how tall this berm is. So what we do is we scan it with a very high precision 3D laser scanner, and we use that data, that very detailed engineering data, in order to give each team a score for their run. 3 minutes remaining. I wonder how the students know when to stop, or if it's just timed, or if they're actually looking at data, or if they're looking at a camera view, since the sides of the diggers are see-through, or if they're just looking from a camera, like a lander camera, to see how deeply the drums get embedded beneath the surface. Seems like there's lots of options there. We're down to the 2-minute mark for University of Virginia. This is their final run. So this is what's going to determine their standing in this event. Oh, that orange side is really slow to raise. It might be the fullest we've seen. The fullest, is fullest a word? Wait, there's a hill right there. They've dug quite a hole right there. Look how big of a hill. Oh, they didn't tip over, so they must not be too heavy on the orange side. There's a rock. Is that a rock in the orange drum? That may be a rock. If that rock doesn't drop out, that will be some wasted energy and wasted effort, because it won't end up giving them any points. All right, with 30 seconds left, this may be their last. This is likely their last cycle. But I believe the students are going to be happy with this. I mean, I'm pretty sure they were happy with yesterday's run, even though they lost a wheel and weren't able to get that much material into the scoring zone. And as time runs out, let's give University of Virginia a big round of applause for a job well done. They should be really proud of that. Next up is going to be University of Utah getting a second run. University of Utah coming up next here at NASA's Lunabotics 2026 Robotic Construction Competition. The University of Utah is about to start their second and final competition run here at NASA's 2026 Lunabotics competition. Their robot is all set up and ready to run in our Lunabotics arena. The students are all set up and ready to push buttons in mission control room. And we're just waiting for the judges to start the timer, which is just about to happen. All right, 20 minutes for University of Utah. You can see that black and white barcode. Two of them on the screen. Robots often use these barcodes in order to localize, which is a fancy word that means figure out where they are. If you tell a robot that a barcode is in a certain place in 3D space and is a certain size, and then you point the robot's camera at that tag, it can use math and trigonometry to figure out where its camera is in relation to that barcode. Pretty cool technology. A lot of the robots in this competition use that technology in order to keep track of where their robot is in the arena. And robots all over the world, honestly, in factories and other places where we can control the environment by putting barcodes in specific places, use that sort of technology. I use it all the time on my robots. Not even joking. All right, there's the first bite for University of Utah. They're going to bring it up and over and on board. I'm guessing this is autonomous because a human driver wouldn't give up after one tiny little scoop. I don't mean give up, I mean go to the scoring, but an autonomous robot would totally do that. This robot is going right towards some rocks. And I see the students are hands off. They're watching an overhead camera and they're hands on, so they may have just turned off autonomy. Now I see hands on joystick. Now they're stick driving this robot. So that appeared to be an autonomous dig and then an autonomous traversal through the obstacle zone, but since the robot went straight toward that rock and started trying to climb over it, the students look like they decided to abort the traverse autonomy. But now that they're in the vicinity of the scoring zone, they may be setting up for autonomous dumping, autonomous delivery. Not sure. Either that or something died on their robot and they are going to start it back up again. I see typing on the keyboard. As a software guy, I feel the pain. I've experienced it. Looks like their front loader is working, but obviously the student is wanting to drive this robot backwards in order to back into the scoring zone before dumping the material that is on board, or the student is attempting to activate autonomous dumping. I see more typing on the keyboard. The students are not panicking. They are cool, calm, and collective. There we go. The student is basically going to the far corner so that when they dump this material, it won't be in a spot that is in their way later. All right, that's the first load. Now that we've got that out of the way, the students are likely going to either try another autonomous dig, traverse, dump cycle, or they're just going to say, that's enough autonomy, time is running out, let's just do the rest manually. Okay, they're in the digging area. They are pointing at directly towards a rock right now. Are they going to try and dig towards that rock? That's a rock on top of a rock. I'm pretty sure the students can see that because they have the overhead camera right in front of them. This appears to be a purposeful. They got the top rock, and are they going to go deliver that, or do they want this in their dump bed? I think they do. Look at that. I was wondering if they would just drive with it in their bucket loader. Okay, they got that one's bigger. Sorry, I'm trying to control the camera and I panicked. Alrighty. Is it even gonna fall out? Oh my goodness. Okay, they can probably just leave it there, right? They can just drive. Oh, there it goes. Just like a good old-fashioned dump truck, man. All right, now they're going for more. Now they're going for the granular material. All right, let's see how much they load this thing down with just under 13 minutes remaining. They haven't gotten any huge bites. Okay, they're gonna go and deliver these 2 rocks and this granular material into the scoring zone. All right, Utah. I believe this is the first rock delivery of this year's competition. Look at that. Boom. That's a mic drop moment right there. Take that, silly rocks. You don't scare us. We're Utah. We eat rocks for breakfast. Okay, the robot has stopped and students are typing on keyboard. Okay, joystick is picked up and we're driving again. Oh, a lot of that material is just getting stuck in their front bucket loader. It's just not flowing out into their rear hopper. or their dump truck. It's only like the top layer that's coming out. That's too bad. They're pushing hard, but only getting a little bite each time, it looks like. It's just getting stuck there. This material does that a lot. Although that could be just a very thin layer that's remaining. It's hard to tell from this angle how thick that layer is that's just not coming out. It could be just very thin, which isn't a big deal, honestly. The back of their front bucket may have some texture. It may have some. It may be not smooth and just enough texture to hold on and kind of capture these small particles and keep them from flowing nicely. All right, heading back. This is a nice amount of material. Once again, the robot stopped. Okay, it's moving again. They're going to end up covering up those rocks. We won't be able to see them soon. The laser 3D scanner will see them though. It will see the volume that they take up, which is what we are using for scoring. Digging in a slightly different location this time. Starting back further. 8 minutes left. I just wish that each bucket had a little more in it. Just getting little bites each time. They're hitting a lot of resistance when they're pushing in. I don't know if their wheels are just not getting a lot of traction and not pushing as hard as we think they're pushing or want them to push. Okay, that was better. Maybe. This is the problem that all of these teams, all of these university teams have to solve, is how big to make their robot, how strong to make their robot, how powerful to make their robot while still meeting the requirements. Because having a big, heavy robot can actually be a disadvantage, at least for the overall prize, which takes the mass of the robot into account. Six minutes left for Utah. This is their final run in this competition. All right, 4.5 minutes remaining for Utah. And it looks like we're just going to have time to do one more team after Utah is finished. We're going to just barely have time to squeeze in University of Illinois Chicago after Utah is finished. All right, 4 minutes, just under 4 minutes remain for Utah in their second and final run. They're making a pretty deep trench right there. Looks like they're picking a slightly different angle this time. Nope, they're falling right back into that same spot, just fine. Although they might find looser material if they went to the side a little bit, honestly. Their dump bed is pretty full right now. One minute 40 left. 1 minute 40 left. This robot seems to have paused. Here it comes. A minute 20. Might be enough time to do one small load. One minute left. Is that all they're going to do? They're afraid to take another. No, yeah. Students don't think they have enough time to take another bite, so they're going to head and go dump what they had. Whatever is going on with the robot, they're having to that happen again and waiting for it to start up again, and now they're driving again, and they might make it in with this last load just in time. And they just made it with 10 seconds left. Let's give University of Utah a big round of applause. That was their second and final run. They should be proud of what they've done here in Lunabotics 2026 finals. Now, we are going to quickly reset the bin and remove the Utah robot and put in the University of Illinois Chicago robot, and that will be the last run of the day. Thinking ahead to tomorrow, we will run the rest of our teams, which is Michigan Tech, New Mexico, University of Alabama, San Diego State University, Virginia Tech, and Iowa State. So that is the plan for the rest of today and tomorrow. You're watching NASA's 2026 Lunabotics competition, streaming live from NASA's Kennedy Space Center in Florida. The University of Illinois Chicago is going to be starting their second and final run here in just a few minutes here at NASA's 2026 Lunabotics competition. This week here at the NASA's Kennedy Space Center Visitor Complex, we have the 10 finalist teams out of 47 teams that competed last week at the Lunabotics qualifying event. And during our 3-day finals event, which was yesterday, today, and will continue tomorrow, these 10 teams are competing against each other, although each getting their own individual run, 2 runs each in our simulated lunar soil bin. These robots are basically simulating just being dropped off of on the lunar surface from a lander, and the robots need to dig up this simulated lunar soil and deposit as much simulated lunar soil into the scoring zone as possible, thereby creating a berm or a protective barrier on our simulated lunar surface. You can see there are several rocks placed around, strategically around our arena, that these robots are going to want to avoid. Some of the rocks are small enough that some of these robots could actually pick up and carry into the scoring zone, which we saw in the last run. The prior run, which was Utah. We gave each of these 3 finalist teams 30 minutes to perform these tasks in their first run. Due to some time constraints and running a little bit behind schedule, the chief judge and judging team have decided that all of the second runs for these robots are going to be limited to 20-minute runs. And we're off. 20 minutes is now ticking down for University of Illinois Chicago. First thing the students did was turn the robot around. It was facing in a direction that they were not satisfied with. And it looks like they're going to back up towards the wall and start their first dig right there. You can see their center-mounted digging hopper lowering so far down that the wheels on this robot lifted up into midair. They have a vibrating motor on their digger that helps loosen the soil, this very compact, very heavy soil. And that was autonomous because the students, all 3 of the students, had their hands clearly behind their heads during that digging pass. This traverse is being stick driven though. There's a good amount of material on board right now. Look how full that center mounted hopper is. This robot is really heavy right now, having a little bit of trouble maneuvering. Okay, their hands free again. It's funny watching these students put their hands behind their head. It's almost like they're being arrested when they're doing autonomous operations. It's like synchronized. Okay, hands are still off, and now they're back on the joystick. So the Chicago team has performed both a digging pass and a delivery pass or a dump autonomously. So they've got to be happy with that. That gives them some bonus points over any team that has not attempted those operations. All right, now the student is stick driving the robot back into a starting location, and we'll be able to tell if they start another automated dig or not. Maybe. The student is still holding the joystick, but I do not see any buttons being pressed. So the judge in the mission control room knows for sure whether that counted as automation or not. Automation or not, that is a nice load right there. That bucket could probably hold a little more, but I would be happy with that, what's in there right now. So with 16 minutes remaining, that means in the first 4 minutes, this robot has completed 2 full cycles, at least partially automated. All right, the student is manually setting up for the 3rd cycle. So this behavior is a little worrisome. Some of the wheels may be just freewheeling. In this view, the wheels on the right are obviously driving. I fear that the wheels on the left are just not reacting in the way that the student is commanding them. All right, they're gonna try a dig right here. Let's see if this robot goes straight. No, it's not going straight. I think the one side of this robot has just stopped responding to commands, possibly. 13 minutes left in this run. Plenty of time for the students to troubleshoot the problem and have an opportunity to reset something. Restart something. However, if the solution is a blown physical fuse or a physical type of circuit breaker where you have to actually flip it with your finger, the students' hands are tied during the competition. They're not allowed to touch the robot. Meanwhile, the robot is getting buried deeper and deeper, at least on the side that has active wheels. I was about to suggest that if the students keep pushing it like this, they could high center the robot, but this robot's chassis is so thin and absent with that digging bucket in the air. There's really not much of a chassis to even high center on. How deep can this robot actually bury itself if it tried, I wonder? 11.5 minutes remaining for these students to consider the situation and try different options to try and recover. This University of Illinois Chicago team actually came in first last year for robotic construction, meaning they actually built the biggest berm last year in this competition in Lunabotics Finals 2025. They did not win overall, possibly because they didn't have as much autonomy as some of the other robots. And autonomy is worth a lot of points in the overall prize. This team did add some autonomy this year, which we were able to witness towards the beginning of this run. So I suspect that was an attempt to not only win robotic construction, but have a chance at winning the overall prize. Sadly, something apparently has broken on this robot, causing the right side, or the far side from this camera's perspective, to stop working. And apparently this is a failure mode that the students in the control room are unable to recover from. We can see a judge leaning in, looking at the power measurement, and the students have called this run early. So I want to give the University of Illinois Chicago team a round of applause. They did really great. They were having a great run. They had a good run yesterday. They were having a pretty great run today before this failure. But sadly, just didn't get very much material into the scoring zone. That said, that is the end of our missions, our competition runs today. So, looking ahead for tomorrow, we will not only start our broadcast at 8 a.m., but we're going to start our first competition run right around that same time tomorrow morning. We're going to start a little bit earlier tomorrow than we did today. And the teams that are going to run tomorrow are going to be, after Chicago is Michigan Tech, then New Mexico, then University of Alabama, then San Diego State University, then Virginia Tech, and then Iowa State. We have all of those teams to run through tomorrow. We're starting a little bit earlier tomorrow than we did today in an effort to make sure we can finish in plenty of time to give a large multi-hour possibly break between the last run and the beginning of our award ceremony tomorrow. That gives these student teams plenty of time to pack up all of their stuff, get it all moved out of here, and come back and have an enjoyable award ceremony. So that is the plan for tomorrow. You don't want to miss it. Set an alarm. Make sure you're here in time. For those watching remotely, we will start again promptly at 8 a.m. tomorrow morning. So set an alarm. Don't miss it. Thank you for watching day 2 out of 3 days of NASA's Lunabotics Lunar Robotic Construction Competition. We will see you all tomorrow. Get a lot of rest tonight. Don't stay up all night, students, okay? We got to compete tomorrow, right? All right. Good night, everybody.